Hey everyone, my name is Lance, and today I'm going to be trying to explain resistance in a wire using the resistance in a wire simulator on the Physics Education Technology website. Let's get started. So, the first thing that we're going to talk about is this equation here, big scary equation R, capital R, as the variable we're solving for. This is the resistance, and this is measured in ohms. This is the resistance of this specific conductor at this length and with this area, of course. Um, Measured in ohms, like I said, 1 ohm is the resistance that causes 1 volt of electrical potential to produce 1 ampere of current. And this equals rho times length divided by area. And these are all measurements of the conductor itself, okay? Let's start with rho. Rho, or represented by this small p symbol, represents resistivity and is measured in ohm meters or ohm centimeters in this case. Basically, resistivity is how difficult it is for the flow of electrons to pass through a length of conductor. Okay, so it's ohm meters. This is ohms. So this is the overall difficulty of flow of electrons to pass through a conductor. This is the difficulty of the um, flow of electrons to pass through a length of conductor. Okay, a certain length. And is multiplied by the length, the overall length of the conductor. And this length is measured usually in meters, but in this case, it is centimeters. And lastly, we have A, which is our cross-sectional area of the conductor. In this case, it's a circle. And it is measured in square meters or square centimeters in this case, in the simulation. As you can see, our resistance right now with these criteria is 0.667 ohms. Okay. Well, let's see what happens when we increase resistivity. Our resistance increases, meaning this is directly or linearly proportional. Resistivity is linearly proportional to resistance. The same with length, since it's on the top of the fraction symbol, but we'll get there. What influences resistivity? Well, what are these little black dots in the wire that are being added or subtracted as we move the slider? These little black dots represent disturbances, or you could call them points of collision or points of resistance that an electron flowing through this conductor will experience. Okay, so things that influence resistivity are electron availability, basically how many valence electrons are free to move to create that sea of electrons that allows current to pass through a wire. Materials like metal, especially materials like copper, will have a lot of free electrons, free valence electrons, to help create that sea of electrons, right? That flow of electrons. A material that doesn't have many valence electrons is not going to be a good conductor. Another thing, or we could kind of lump all of these into one big category, which is disturbances or points of collisions in quotations here, because nothing's actually colliding. Um, so as electrons move through this wire, they're going to encounter nuclei of the atoms in the material. Nuclei, as we know, or atoms, have an electrical field, and this is going to cause a scattering, or it's going to influence the path of electrons, rather. Inner electrons, so non-valence electrons, these are going to cause a repulsive effect to electrons flowing through the wire. And lastly, impurities, crystalline. These metals are crystalline, or solids are crystalline structures. So any imperfections or impurities within the crystalline structure are going to cause another point of collision or resistance, or another point of disturbance for the flow of electrons. And lastly, these little black dots can also represent, or what influences resistivity is lattice vibrations. So, as you know, atoms that vibrate in place, right? And as temperature increases, as you insert more heat energy into a system, these vibrations also increase. They'll vibrate faster. And these will cause disturbances. These vibrations will cause disturbances in the surroundings that disturb the flow of electrons through the conductor, which brings us back to rho being temperature dependent. Resistivity is directly influenced by increase or decrease in temperature of the conductor because, like I just said, and as we know from chemistry, atoms will move faster. The molecules will vibrate faster if you insert more heat energy into a system. Okay. So the reason that it is material dependent, rho is material dependent, is because each material has a different number of free valence electrons. And the reason it is temperature dependent is because of lattice vibrations. Okay, so these little black dots represent all the little things that can impede or disturb or scatter the flow of electrons. And as you can see, like I said, it is directly proportional. Length is also directly proportional because as you increase length, you have farther to go, you have more of these impurities, more of these nuclei, these inner electrons to pass by. And you would think area would also be proportional, but it's actually inversely proportional. That's why it's on the bottom of this fraction symbol. And it is because as you increase the area of the conductor, you have more pathways to move around all of these little black dots. If you, being the current or flow of electrons through the conductor, you have all these little pathways that have now widened or opened up that allow you to bypass these little black dots, these little impurities, points of collision, whatever you want to call them. As you decrease area, resistance becomes huge, right? Like you will not pass a current through this conductor because the area of the cross-sectional area is so small that there's no pathway around something like this little, let's say this is an atom's nuclei. There's no pathway around it. How is an electron supposed to get past this electric field, right? So yeah, that is basically resistance in a wire. And the resistance in a wire simulation is a great tool. And it allows you to visualize the relationship between all of these variables very nicely. Thank you so much for watching, and I hope this was informative.